Now's the time we're actually going to start solving logarithms and also exponentials using logarithms. Because remember, these are inverses. This is the way you can actually solve some exponential equations that are difficult. So we've solved exponentials that had nice answers that were easy. These ones are a little more challenging, and I'll show you what I mean later. Let's start with logarithms, though. When it comes to solving logarithms, remember the inverse to a logarithm is an exponential. So to undo a logarithm, you can do an exponential to both sides. You just need to make sure you use the exact same base. So we've got a base of 2, and the undo it, what you do is you do a base of 2 on both sides, and you make both sides of the equations exponentials. What that does is when you have 2 log base 2 of x, for instance, remember this log is telling us 2 to what power gives us x? Well, it is the power that's going to give us x. And this might be confusing, so this whole thing is actually going to be x. Because remember, this is the log base 2 of x is telling us what exponent's going to give us x, and we're raising 2 to that power. So as confusing as that is, what happens is that actually just cancels those out. And you get 3x minus 4 equals 2 to the third, or 8. And then you'd add 4 to both sides, and you just solve this like a normal equation. Divide by 3, x equals 4. Now, the one thing with solving logarithms is you always need to check for extraneous solutions. And the reason you have to do that is because there are domain restrictions, and you only actually ever do that for functions that have domain restrictions. So in the past, we've done it for rational functions, so the ones that were had a denominator. Remember, you can't have a x value that's equal to 0 on the denominator, or it's not x value. You can't have the denominator equal 0 on the bottom of a fraction. So we would have extraneous solutions. Same thing here. We know that the base and the argument can't be negative, so you just have to double check that 3 times 4 minus 4 is actually greater than 0, and it is. So that's what you're doing. You're just checking the argument, making sure you don't get a negative base or negative argument. So same thing with this next one. Remember, to undo a logarithm, the inverse is an exponential. So I take the base, which is x, and I make that my base for both sides. And that goes away, and I get 49 equals x squared. So then I'll take the square root. Just remember, when you take a square root, you have a positive and negative answer. So x is equal to positive and negative 7. But then we need to check. So the x is in the base, so we don't want negative 7. We just want positive 7. Negative 7 is extraneous. You don't need to write that on your answer. I'm just writing it for your sake. And that's because negative 7 would give you a negative base, which is not allowed. Let's do a few more. Now, when it comes to what I'm doing, the only reason I can do it the way I'm doing is because there's nothing added or subtracted after the log. In this case, I've got this negative 7, so we do have to isolate the log first by adding 7 to both sides. So you have log base 3 of 2x plus 1 equals positive 2, and then we can do our little base trick. So the base is 3, so I'm going to undo the logarithm by doing an exponential because they are inverses. So then I have 2x plus 1 equals 3 squared, or 9. So I'll subtract 1 from both sides. So 2x equals 8. And if you divide both sides by 2, you get x equals 4. And then I just double check. 2 times 4 plus 1, is that greater than 0? Because that's my argument. I have to make sure my argument's always greater than 0, or it's positive, and it is, because that gives me 9. This problem, the log is already isolated, so I don't have to add anything over. So once again, I can use my exponential rule by matching the base. The base is 3. Those cancel, And I have x squared minus 5x plus 3 equals 3 squared or equals 9. Now this is a quadratic, and there's a quadratic term and a linear term, which means I have to subtract the 9, get it all equal to 0, so that we can solve by factoring. So I'll factor this to x minus 6, x plus 1, oops, and then find my 0. So I've got x equals positive 6 and x equals negative 1. Now once again, like I said before, you always check for extraneous solutions. So I'm going to take this x squared minus 5x plus 3. So I'm just taking the argument. And I'm just double checking, is that actually greater than 0? Well, that's 36 minus 30 plus 3. So that gives us 9, and 9 is greater than 0. And then for this other one, negative 1 squared minus 5 times negative 1 plus 3, is that greater than 0? We get 1 squared plus 5 plus 3, or sorry, 1 plus 5 plus 3. Well, all of those are positive, and that's all 9, adds up to 9. So once again, that one works. So both of them are just dandy.